10.4 polar coordinates. I have taken 10.4 and broken it up into two parts. This first part is just getting you comfortable with polar coordinates. The homework that's associated with this first half of the video series is 5 through 43. Just do every other odd. You're going to be simply learning how to go from rectangular coordinates to polar and back. So, polar coordinates, you have r, which is a directed, and that's important, distance from the origin. Here's your directed line segment, and it can be at any angle theta. And theta always from standard position rotates from the positive x-axis and around clockwise. So what we can do is we can rotate, and I'll erase this, you can rotate to a particular angle and then go out a particular distance in that direction, and you have your point r theta. And it's really important that you practice. So, yeah, you're going to get lots of practice. Okay, now the book often refers to the pole, and the pole is just the origin, and it can be any angle. It's just where r equals 0. Okay, now to go from one to the other, say you're given the distance from the origin and the angle of rotation, r theta. To change that to x's and y's, think about what you have here. Here's the origin. You've rotated through theta degrees, and you've gone out r units from the origin or the pole. Now, you see that that creates a right triangle where this distance is x value, that distance is y value, the cosine of that angle is x over the hypotenuse, sine is y over r. So that gives us our equations for finding the x and y values in rectangular form, where x is just r cosine and y is r sine. Very, very important that you get that down. Now, going the other way, say that we're given the x and y coordinates and we want to find it in polar. Well, if this point is xy, then this is x, this is y, and you can find r using the Pythagorean theorem. X squared plus y squared equals r squared. And if this is theta, then opposite over adjacent, y over x, is our tangent. So you can find the tangent, or the theta, by using the inverse tangent of y over x. Now, this right here, you're going to know what quadrant your point is in. The inverse tangent only gives us minus pi over 2 to plus pi over 2. So if you're in quadrant 4, you're going to want to add 2 pi to make it, if you're in the negatives here, you want to add 2 pi to make it a positive theta. But what if you were in quadrant 2? If you do the inverse tangent in your calculator and you get the angle is minus whatever, you're going to add pi to that to be in quadrant 2, because the calculator is only going to give you these two. You're smarter than your calculator, okay? If your point's in quadrant 3, the calculator will give you quadrant 1. You have to go pi units around. So keep this in mind right here, that you know what quadrant you're supposed to be in, and you have to do the required adjustments. Along the same lines there, if we have the point where r is positive and we're at some angle theta, we can go backwards on that radial line and be at a difference of pi from that point. For instance, look up at this original. If I rotate to theta plus pi, that's down here, and I could find negative, I could rotate around to here and go negative direction for r and get the same point. So you can always find at least two principal values of your r. R theta or negative r and theta adjusted by by a pi, either forward or backward, so plus or minus. And you can find an infinite number of coordinates for the exact same point by taking whatever theta is and just going all the way around the circle, forward or backward, as many times as you want. And you'll end up in the same place. For instance, this point right here. If I go all the way around the circle, I'm adding 2 pi. I end up where I was. Or I could go backwards and I end up where I was. Or I have the choice of going backwards on the radial line, r units, at a pi offset, like I just showed you. Okay, examples. Going from the rectangular to the polar, this is x, this is y. So r, by the Pythagorean theorem, I can square the x, square the y, add them together, take the square root. It's just the Pythagorean theorem. So I am root 10 units from the origin when I'm at this point. Let's see this. Here is my r. And now I want to find my theta. But if I stick this in the calculator, it's going to give me this. So you see, I need to go all the way around the circle. So I'm going to take whatever the calculator gives me and add 2 pi to it because it's going to give me a negative angle. And that's okay. It's just not what we call the principal value, which would be from 0 to 2 pi. So, or yeah, you know what quadrant you're supposed to be in. This says that you're in quadrant 4. So you need to find the angle that's in quadrant 4. If you choose to do negative r, and this is not your first choice is positive r and between 0 and 2 pi for your angle. But if I was to go backwards, let's take this radial line here. I would rotate around to there and go backwards root 10 and end up at that same point. All right? There we go. Now, polar to rectangular, if I'm this many units from the radius, that's my hypotenuse, and my angle of rotation is at pi over 3. So let me draw this. I have rotated to pi over 3 and gone out 3 units. And there's my point. This is theta, pi over 3. R is the distance. But if I drop that line straight down, you see that the x value is this distance and the y value is that distance. Theta is in the middle. So the cosine of pi over 3 is x over r. So if I multiply by r, I get x. So x is r cosine 1 pi over 3. This is a half, so 3 halves. The y value is our sine. Sine is root 3 over 2 multiplied by the 3, and I have my point, plain and simple. You'll also be asked to convert equations from rectangular to polar and from polar to rectangular. So there are certain things that you need to look for, and I'll call them tricks, but they're not. They're you knowing what you're doing. So in an equation like this, you know this is a circle centered at 0 with a radius of 3, right? But you see x squared plus y squared, automatically change that to r squared. And in this case, you don't have to do anything to the 9. He's just a number. So r squared equals 9 is the same as r equals 3. And you can see by the graph that there's no relationship here with the theta. So it doesn't depend on theta. Theta can be anything. Your radius is a constant 3 units, and we're going to just pretend that this is a circle here. I'm not a good grapher. Okay, next problem. I have x squared and y squared, but there's subtraction. So this is not a circle. We look at this and we know that it's a hyperbola because the x squared is positive, it's horizontal. Divide everybody by 9 to make this a 1. That means that this x squared will be over 3 squared, y is over 3 squared. So a and b are both 3. My center is 0. I go out 3 units in all directions from the origin, which is the center. I make my box. I draw my asymptotes, connect the corners through the center. Remember, this is from earlier this chapter. The x squared was positive, so my vertices are along the horizontal axis through the center, and I just pass through the point and approach the asymptotes, and I get that hyperbola. So this is how it's graphed. How it's converted, we've got x is our cosine, that's squared, y is our sine, and he's squared, and it just equals 9. So I'm going to square the r and square the cosine, square the r and square the sine. Now I can factor an r square out. That leaves me with this, and you have to know your trig. All right, so we have to remember that cosine squared minus sine squared is the cosine of the double angle. So I replace this with this using that identity. And if I divide both sides, the point is to solve for r, right? So I'm going to divide both sides by the cosine of 2x, which gives me the secant of 2x on the other side. Take the square root, and I end up with r equals 3 square root of the secant, and that is hyperbola. All right, with this one, we've got x squared plus y squared, which we automatically changed to r squared. Oh, I didn't, did I? That's okay. It'll turn out. This guy right here is 2a r cosine theta. So we end up with r squared minus 2a r cosine. Factor out an r, and you'll see, I need parentheses right there. Factor out the r, everything equals 0. You're going to set each of these factors equal to 0. So r equals 0 is the pole, and this happens a lot, but he's usually a part of the graph of the other bit. So setting the second factor equal to 0 gives me r equals 2a cosine. We've done this before. This is a circle. Because this is cosine, it's on the x-axis, right? When the cosine is positive 1 at 0, r is 2a, so you have a point right here, okay? When you're at pi, the cosine is negative 1, so here's pi, but you're going to go backwards to a and make a point. When the cosine is 0, at pi over 2 and 3 pi over 2, right here and right here, r is 0, so you're at the pole. So you're going to start at 0 where you're here. You're going to rotate through to pi over 2. You're going to rotate through quadrant 2 where r is negative, which puts you over in the opposite. So you end up with this circle. And the way I know it's that circle is looking at the original. If I group my x things together and I complete the square, I take half of 2a, square it, and add it to both sides. This is a perfect square, x minus a squared. I have y squared. That is the equation of a circle centered at a, 0, with a radius of a. So here's the point a, 0. I'm going to go over a, backwards a, up a, and down a, and connect my dots. All right, graphing with it in this form where we go through our angles, we'll do that kind of the same way we did the parameter graphing in the next video. The equation x equals 12, that's just a horizontal line. Oh, yeah, that's not the right graph, is it? I caught myself. You didn't see that. Ha 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 ha. Okay, this graph, x equals 12, right there. Ha ha. There you go. So, sorry about that. You'll do it too, so give me a break. X equals 12. X is just our cosine theta. So dividing both sides by cosine, we get the equation r equals 12 secant, and we get this radius, right? We get this graph right here. Cool thing about this, when we start graphing, going through the values, the secant, its principal values are defined. This is 1 over cosine, right? So if I look at, I'm going to draw a cheater circle here. Where is the secant defined? Well, it's not defined here and here. So if I rotate from minus pi over 2 through plus pi over 2, I'm going from the cosine being 0 to 1, and then through the positives and back to 0. They're all positive. 0 to 1 and back to 0. So the secant is infinity to 1 to infinity. So my r values here are going to go from 12 times infinity down here as my angle is approaching negative pi over 2. This is getting larger and larger as far as the distance from the origin. Then when I'm at 0, r is 12. And then as I move, the denominator gets closer and closer to 0, the secant gets closer and closer to infinity, so my distance from the origin goes to infinity as I approach pi over 2, if you can imagine that. Okay, that's why that works. All right, erasing the evidence. That takes too long. Okay, next example. We are going from polar to rectangular in this case, and we have the angle is a constant, and there is no r in this equation, so the distance from the origin has nothing to do with the angle. It goes from minus infinity to plus infinity. We rotate to pi over 3, and we mark that radial line, and we just get a straight line that passes through the origin or through the pole. If you think about the tangent of theta as being y over x, and we're taking the tangent of pi over 3, we have the equation root 3 over 2 over a half, which simplifies to be root 3, equals y over x, our tangent. So y equals root 3x, and it's just that straight line. Taking the equation r equals 5 cosine. This is something that it seems like you're pulling straight out of the air, but it is a very, very useful tactic. So I'm going to take this equation and multiply both sides by r, because r squared is defined as x squared plus y squared, and r cosine is defined as an x. So putting this in standard form here by grouping the x's together, taking half of the 5, squaring it, adding it to both sides of the equal sign, and then plus the y squared, you see I have the standard form of a circle right here. Centered at 5 halves, 0, radius 5 halves. So I'm going to mark that 2.5 there. I'm going to go up 2.5, down, backwards, forwards, connect the dots. And you see right from the get-go, If r equals a multiple of sine or cosine, I have a circle centered on an axis. If it's cosine, I'm centered on the x-axis. If it's sine, I'm centered on the y-axis. And the maximum that a cosine can be is +1, so the maximum my radius can be is that 5 right there. The minimum that this can be is -5 at over here at pi. So as I rotate through to pi, I'm going to go backwards and get that guy. Where r is negative in quadrant 2, all of my points will be at the opposite radial line, and they'll all be graphed in quadrant 4 because they're all negative. Starting at 0, I graphed through the first quadrant all positive values until I got to pi over 2 where it was 0. And then as I rotate through quadrant 2, r's are negative, and I go back to where I get to pi, and I'm at -5. So you see, going from 0 to pi gives me this circle, and you'll see that better in the next video. Next equation, r equals -6 cosecant. Multiply both sides by the sine, and I get r sine, which is y, equals -6. Y equals -6 is down here. Simple, right? Next example, cotangent is cosine over sine times 1 over sine gives me this. Multiply both sides by sine squared, and then we pull that little trick out of our pocket where we multiply both sides by r. That gives me r squared sine squared, which is just y squared. R cosine is x, and you see that I've got this sideways parabola with the vertex at the pole.